So when we finish talking about dark matter, and the next subject is antimatter. And antimatter sounds something like that would show up only in science fiction movies, but they're real, they exist, we can make it, and we can also use it. So what is it? Well, first of all, one theme of my lecture here is that the absence of antimatter in the universe seems to have a lot to do with the neutrinos we talked about in some of the previous lectures. And just by looking at the number of neutrinos, we believe that they must have played some very important role. So we looked at this universe, the picture of the universe already many times, but if you just look at the number of particles in the universe as we know now, it looks something like this. What we are made of, electrons, protons, and neutrons, and even the predominant dark matter is way down here, but the most abundant matter particles in the universe is actually neutrinos by a big margin of almost a factor of 1 billion. Of course, universe has a lot of light, and this light is in the form of photons. There is a tiny particles, the particles of light, and they mostly come from the Big Bang itself, and that's the cosmic microwave background. So these photons are slightly more than neutrinos. If you go out to any empty part of the universe, there is still photons, like 400 of them per cubic centimeter. That's the size of a sugar cube. In the same size, you're supposed to find about 300 neutrinos in the same volume. So the universe is actually filled with neutrinos. There's just tons of them. So even though they weigh very little, altogether they can contribute to the energy budget of the universe as much as all the stars combined. So given this sheer number of neutrinos, at least we get a sense that they must have played some very important role in the evolution of the universe, which may have to do with the absence of antimatter in the universe we observe today. So what is an antimatter? For every particle we know, like electron, proton, there is an antimatter counterpart. An antimatter particle or antiparticle has the same mass as the particle. If they're not stable, they have also the same lifetime. But many properties are the opposite. They have the opposite electric charges. For example, electron, which is in our body, and we use that a lot in our electronics these days, they have negative electric charge. And its antimatter counterpart is called positron, that has a positive electric charge, hence the name positron. In the case of proton, that's again in a body that makes up the atomic nucleus, the proton has an antiparticle called antiproton, not a very creative name, and the proton has a positive electric charge and antiproton has a negative electric charge. Neutron also makes up atomic nuclei. Neutron does not have an electric charge, hence neutron, right? And its antiparticle is antineutron, and no electric charge, 0, and its opposite is also 0, so antineutron does not carry electric charge either. So this way, for every particle that exists in the universe, there is an antiparticle counterpart with opposite electric charges. So this is the first example of artificially created antimatter. So this was done back in 1933, and the experiment was done by setting in a powerful light called gamma ray into this photographic film, and by interaction of the photon with something else inside the film that created a pair of particles shown in yellow. One of them is electron, the other one is positron. You can tell which is which because in a magnetic field, the electrically charged particle would bend, but which way it bends depends on the sign of the electric charge. So you can tell which one is electron, which one is actually a positron. And this experiment was done by Irene and Frédéric Joliot-Curie, and they were also Nobel laureates, not for this discovery, but they have done many other important works in science. And the first example, antiproton, was produced in Berkeley on a hill, and this place is called Lawrence Berkeley National Laboratory. They built a much bigger particle accelerator, the biggest in those days. It still looks now small, but it was the biggest at that time. And this picture shows the creation of an antiproton. So what you do is accelerate protons inside this ring. You smash protons on target. That produces a lot of particles coming out. And among them, there was an antiproton. And this antiproton came into this photographic film, and because it has electric charge, negative electric charge, you can actually see it. But when the antiproton comes in here, after a while, it managed to meet a proton inside the film, because the film has a lot of nuclei in it. And when the antiproton and proton meet, they go back to energy, they annihilate with each other, and that energy now produced various other kinds of particles. And they look like a star, so this is called the star event. So as you see, you can create matter and antimatter in a pair from energy, because E equals mc squared. And matter and antimatter can annihilate in pairs back to energy, again, because of E equals mc squared. And the discovery of antiproton earned Nobel Prize in Physics to Emilio Segre and Owen Chamberlain. And we can actually do experiments with matter and antimatter fairly routinely these days. So this is the collision of electron coming in this way, positron coming from the other side. They annihilate in the middle, they become pure energy, and that pure energy now materialized into other form of masses, in this case, quarks. So particle and antiparticle annihilate to energy, and energy can create a pair of particle and antiparticle. So that's one very important thing to remember. And antimatter is not just for scientific study, but it's being used at hospitals, for example. And the way you may be able to scan your body to locate the position of a cancer, this technique called positron emission tomography is being used. And as you see, positron is there, and that's an antimatter of electron. So what you can do is to inject a form of radioactive isotopes into your body that actually emits positrons, and you can locate the annihilation of positron with nearby electron by looking for the gamma rays. That's the energy of the light. And that way you can scan your body and identify where the cancer is located in your body, and you may be able to actually use radiation therapy to target that area to kill the cancer cells. So that's what you can do with the positron emission tomography by using antimatter. And this is another picture of positron emission tomography, or PET, of your possible brain. And you can immediately tell that if you're influenced by cocaine, your brain looks quite a bit different from a normal brain. So this is another way of telling you that never abuse drugs like cocaine, which is very bad for you. So anyway, so this is what we know about antimatter. And in science fiction movies, antimatter show up in a different way. For example, this is a schematic picture of an engine of an Enterprise spaceship in a Star Trek movie, and this engine is powered by antimatter. Because if you actually store antimatter and convert antimatter into energy, it's easy to do. You just sprinkle antimatter together with matter, they annihilate and produce energy. And that kind of energy source turns out to be 300 million times more efficient than regular gasoline. So if you're on a spaceship, you'd like to store energy as efficiently as possible. So antimatter looks like indeed a good candidate for that. So that's why the Star Trek movie relies on antimatter for that. And that brings up the question about, okay, what kind of energy sources are more efficient over the others? We always use this unit called electron volt in microscopic physics when you talk about energy. It's a tiny amount of energy. This is an energy an electron gains by accelerated by one voltage. Namely that if you actually have a battery, typically has about 1.5 volt, electron acquires energy 1.5 times this number. Very little, but this is the unit for energy we use. Now, if you think of one single piece of proton, it weighs a certain amount, and you can convert that mass into energy, again, using E equals mc squared. That turns out to be about 1 giga electron volt, 1 billion electron volt, and we call this unit JeV. And for typical chemical reaction, like burning fuel, or even dynamite or gasoline, the typical energy you get is about 1 electron volt. That's about a thousandth of the mass of the proton. If you use nuclear fission reactors, you typically get 1 million electron volt, or MeV. That's about a thousandth of the mass of the proton. This is the billionth, this is a thousandth. So you see that nuclear fusion is about 1,000,000 times more efficient than burning fuel. Nuclear fusion might be 10 times more efficient than nuclear fission, so you get 1% of energy of the mass of the proton. But if you use the annihilation of matter and antimatter, you can fully convert the mass of the proton into pure energy. So you use 100% of this, so that would be about a JeV of energy, 100 times more efficient than nuclear fusion, billion times more efficient than the chemical fuel. So that's why the antimatter can be very useful, but also can be very dangerous. In a novel by Dan Brown, Angels and Demons, and this also became a Hollywood movie starred by Tom Hanks, the antimatter shows up. So this antimatter had apparently been produced at the European laboratory CERN, where LHC is running. A scientist, according to the novel, produced 1/4 gram of antimatter without the knowledge of the Director General. And this amount of antimatter falls into the wrong hands, and some people get threatened using antimatter as a weapon. And that, of course, doesn't sound very good. Now, the thing is that the Director General didn't apparently know that scientists produced this 1/4 gram of antimatter. But if you do the math, to produce this much antimatter, they must have spent about $1 billion, trillion for this. You need that much electricity for this purpose. And Director General didn't know about it, so that means the laboratory must have a huge amount of budget. I'm really jealous about it. Anyway, that's just a story. Of course, you can't possibly spend this much money to produce antimatter. There's no worry that antimatter would fall into wrong hands, at least for 1/4 gram of it. But how big deal is it? 1/4 gram of antimatter? It sounds so little. It turns out the 1/4 gram of antimatter, once it annihilates with the ordinary matter, produces as much energy as an atomic bomb in Hiroshima. It's no laughing matter. So you can see a tiny bit of antimatter annihilating with matter can produce a huge amount of energy. And that's how efficient antimatter annihilation is if you manage to create this much of it. But as you see, it's virtually impossible to do that anyway. Okay, so now comes the situation of the early universe. So antimatter is indeed dangerous, and you can create pair of matter and antimatter once you produce energy. So early universe must have had huge amount of matter and antimatter, but we need small difference between them, because once the universe expands and cools, matter and antimatter annihilate into pure energy 1 to 1. So all of them pretty much have annihilated away, and this is the remainder that's us. So we clearly won, but we don't know why, and that's the big problem. So how do you think it could possibly have been possible that we survived the Big Bang by this tiny difference between matter and antimatter? Any ideas?